and I think it's not going to work on here. But if you go to this page, if you're interested in iTunes, click, there's help files on here also you can go through. Eventually you'll see a variety of different links. It'll open up the iTunes application. This will never work with the iTunes U app that you can install on your on an iOS device, like an iPad or an iPhone. That's where I was initially getting confused. It only seems to be available through the desktop iTunes application. But that said, that doesn't always work either, as we saw here. If you are successful in getting that far, you'll see a variety of different links, including one that says, I'm just going to cancel that, geography. Obviously, you click on geography, it lists every class regardless of whether the professor uses the service or not, and you'll see a lot of zeros. So you can eventually go to there and click it. It's not going to work. So because of that challenge, I also created a YouTube channel. And to search it, let's make sure it comes up. Some people are having trouble. Try Greg Caniglio SUNY. And here they are. If you click on Greg Caniglio SUNY, this is my channel. Keep in mind, I'm teaching 2 courses, so you'll have to look through for the GEO481. If I knew more about YouTube, I would have split them up, but I'm not a YouTube user. And here we have, look at 15 of you were able to view it. Here's the lecture that I recorded in Florida. I shouldn't leave that out. That's okay, next week I have to go to Detroit, so that makes up for it.
I'm so sorry.
Thank you. So there are 481 lectures. I am recording. Sometimes the very first lecture didn't work. My laptop doesn't like this this smartboard, so I will have to remember again to dual advanced slides like I did last week. But the concept is to do this, not just for when I'm not here, which hopefully is not very often, but to do it every class as a study resource for you. Let me open up the slideshow on this too. We will go through, obviously, since today's February 17th, you might guess we'll go through the February 17th lecture. But I will also, at the end of the class, review all of the material, because next week is the first exam. So it would cover all the material up to and including tonight. At the conclusion of going through the regular lecture, we'll go through all of the classwork up to now. And this is a good chance for me to highlight for you which things that I've covered that I think are most important. And if you read between the lines, the things I think are most important are most likely to show up on the test too. Don't want to trick anybody here. So, the things that are most important are the things I should ask about. So we'll go through that at the conclusion of the class tonight to help you prepare. There will be 15 to 20 short answer questions on the test. No multiple choice or true, false. But no, I remember taking physics classes where one answer takes 2 sheets of paper. Nothing like that either. We're in between. There'll be a few, what I call quasi-math questions. I'll try to pick numbers. I don't want people to be reliant on a calculator. You can use your calculator. If it's a smartphone, just don't bring up Google or something like that. Maybe have me or the TA come by and stand over your shoulder. I trust you guys. But I'll also try to pick numbers, because I want you to focus on the concept, not the math. So I usually try to pick numbers that are easy for you to do in your head and not have to worry about the actual math, but just the concept. So there may be a few questions that would involve light math. Short answer. Some answers might just be a word or two. Some answers might be a paragraph or sketching out a result, but nothing too big. 15 to 20 questions. Hopefully nothing too tricky. Those of you that were here the first week might remember when we were talking about meridians and parallels. You might remember that I mentioned the Tragically Hip, the Canadian band that talked about the 100th meridian, and now you know that that's the 100th degree of longitude. It would be worth it to remember that for next Tuesday. I'll say that. That's a little bonus for those of you that joined us tonight, which is most of you, which is good. There's probably 50 of you here. So there's a good chance of that being the freebie bonus question for the first test. The Tragically Hip talked about latitude and longitude in their recent song. That song's probably 10 years old. So that's what we'll do tonight. I'm going to bring up, I got my first journal, thank you. There are due dates in the syllabus, but you certainly can turn them in whenever, up till the due date. And on UB Learn, to help you out, I posted a sample journal that a student had turned in to me a few years ago in the class. So that's in UB Learn as a guide. As I said then, it's nothing too fancy. The purpose of me doing the journal assignments, I said, is to show you all the different applications. There's a million different ways you can use GIS. I'm interested in you seeing how GIS is used, what types of data GIS data is used, and what type of GIS analyses are used. So if that's what I'm looking for, that should help you think about what I'm looking for in the journal. Just a description of your article, how was GIS used, what data did they use, what analysis was used, and that's really it. And the one that I have already looks great. It's exactly what I'm looking for. Are there any questions? Then I'll start with the February 17th lecture, and then we'll review the course. We'll review the course to date. After that, I mean, if you're welcome to leave if you're confident in the material, but we'll stay as long as we need. And then we'll set you free, and we'll have the exam next week. It's short answers mostly. And then we will reconvene the following Tuesday, which might be March. Is it March something? Well, that's very good. I'm happy about that. That means that spring might be sort of coming. I'm not convinced yet. Those of you not from Buffalo, it's like the worst winter ever. It's not always this bad, although it's usually pretty bad. You should have been here 3 years ago. We had no winter. It's like a distant memory now. That was great, wasn't it? My lawn didn't die. I've never, growing in Buffalo, seen that the lawn stayed green the whole winter. We barely had any snow. I keep desperately thinking of that this winter. It was just 3 years ago, but it might as well have been 30 years ago. Seems like such a distant memory. It was. Yeah, there's all sorts of weather records I could ramble off. There were only, I don't think we ever got a storm more than 4 inches the whole winter. There was only 17 days with snow on the ground, where we just had 40 straight days with snowfall. So it's like two extremes. So yeah, I missed that winter. And the ground didn't freeze, which was, I think, might have been a first. That's right, earliest lake thaw. And last year, I think we had the latest ice on record. May 4th, there were still chunks of ice in Niagara River. I think we're on pace to break. Yeah, right into May, and that was a record. We might be breaking that this winter. But you're right, 3 years ago it was also the earliest thaw, which helps the spring be nicer because the water warms up faster. Anyway, enough weather. Well, it'll be over soon. Another 2 months and we'll be done with it. 3. Okay. I think by now you know which labs you're in. We'll start off talking about relational database models, and I'll mention this as we review on the lecture, on the videotaped, it's not really, on the recorded lecture, I talked about different types of databases. I'm going to focus mostly on relational database. I'll mention that those last couple slides on the February 10th lecture, I'm not going to ask that on the test. I think I'm going to take those slides out for next year. The more I think about it, relational databases are really what I want to talk about. So we'll mention that when we talk about the last week's lecture too. I purposely introduced this into GIS because a lot of GIS people don't really get exposure to database structure. Are there any computer science? A couple, yeah. So you'll know what I'm talking about. Computer science people, this will be secondary. But GIS types like me tend to just work with what we call flat files. You don't work with database, someone sends you a shape file. So here, add this. So I think this is valuable experience to see how data can be optimized. Our IT people in our company are always saying, I wish you GIS people knew more about database structure. So with that in mind, I've decided to add this topic into this course. Because GIS and databases do go hand in hand and work together, especially more and more as technology develops. So in a relational database, I think I mentioned some of this intro last week. A relational database in our DBMS has multiple tables in it. You could have a table of hydrants. Well, let me do this. You could have a table of municipalities, towns. You could have a table of counties, states, countries, streets. Within that framework, you could have a lot of redundant information. If you had a table of streets, the street may have an attribute in it with the county the street's in. If you have a table of towns, the table of towns might also have an attribute with the name of the county. So you're duplicating information. So what we'll talk about is taking that county, making it a lookup table, and then linking the county table to the other tables that it appears in. I think this will make more sense as we go on. I think I use birds as an example here. So in a fully normalized database, each entity or each thing should only appear once in your whole table or your whole database. And we'll talk about reasons why this is important. So here, and then you can bring all this data back together using something called a join. And if I'm not mistaken, you might be working with joins in this lab or the next one. It's this lab, isn't it? So this is good timing for this lecture. You guys learn about joins this week in lab. So just because all the information is separate doesn't mean it's separate forever. You bring data back together using these joins that Torsten and Kajin have talked about in your lab sessions. So here, do I have a slide before that? I don't. I wish I did. This is a table of fictitious bird sightings. That's actually, I'm a birder, so I keep my own records when I have time, which is never. But our company actually does do this. Building various facilities, we're doing environmental reports. We do have people actually go out and record bird sightings for work, not just for fun. Because they're specifically looking for threatened or endangered species of birds, or not just birds, mammals, etc. So here, these are specific sightings indicating the type of species of golden eagle, various information about it, and the observer. So this is the first thing I want to mention. We're going to go through and give different examples of normalization. So here, if you look at the table, of these 10 bird sightings, 4 of them are me. So right away, can you see redundancy? My name occurs 4 times. So that's a waste of database space right off the bat. That doesn't seem like a big deal, but what if this was 100,000 bird sightings and I had 40,000 of them? Suddenly that's a big waste of space. Plus, things can change. What if I change, I'm not planning out, what if I change my name, like Prince, or that, who's that Cincinnati Bengal, no, I'm thinking, Ocho Cinco, changed his name to 85 like his number. And maybe I'm going to change my name after Greg GIS or something. So now if I change my name to Greg GIS, you have to go through the whole database, find every sighting, and change it. That doesn't sound like fun. It's easy to lose data, isn't it? So normalization helps us in those type of scenarios where redundancy and data that changes. What we do with normalization, we create every table has a key that will never change. We'll talk about this further in some slides. So here, I've created a second table called observers. And I've split out the 4 people that have made bird sightings into this observers table. And then in this, you'll see on the next slide, that observer column is going to go away. And talk loud so you can hear me. This table just has the observer ID in it. So for the scarlet tanager, instead of my name, it just says 1. And then that 1 links the sighting table to the observer table where I'm observer number 1. Does that make sense so far? Not only can you kind of see the advantage of doing this, a lot of people at this point protest, Greg, you're making a mess. Can't you just give me 1 table? And a lot of my GIS colleagues say that same thing. And database people will sigh at that point. But maybe you can see why, yes, it's easier to get 1 table, but maybe you can see the advantages against having everything in 1 table. So if I did change my name to Ocho Cinco, I only have to change it here. I don't have to change it in repeated places. Does that make sense? And okay, we're going to talk about that. We're going to normalize an entire database. So one of the things we'll talk about, this kind of frames rules about relational databases. I'm not going to, please do not try to memorize the rules. I'm not going to ask you something memorization like that. If I see something that I think I might ask, I'll give you a heads up. This is meant to kind of introduce some of the reasoning behind a relational database, some of which I just mentioned already anyway. And it's kind of funny how the more things change, the more they stay the same. You hear that? I mean, these rules were developed in 1970. Obviously, technology is a lot different than it was in 1970. I mean, technology is a lot different than it, when I first started this class in 2011. We didn't have things like this, let alone 1970. But what's funny is the concepts are the same. Whether it's a database on my phone or on NASA in 1970, a computer that takes up a whole room in NASA, the concept's the same. And to some degree, these redundancy, some of these things become less of a problem. In 1970, it was a lot more burdensome to store my name 4 times than it is now, with computer memory being what it is. But it still is important. Anyone see? There's a picture going around Facebook of I think it was from a Radio Shack flyer they're going out of business. From 1985, they were selling a 350 kilobyte hard drive. It wasn't even a megabyte. And it was $500. Where this thing has 24,000 times as much memory in it. And I could just drop it in the toilet by accident and it's gone forever. Or worse. You know, someone at work had a little iPod Nano that's like this big. I'd eat that if I'm not careful, if it gets too close to your mashed potatoes. And that had 64 gigabytes in it. So it's amazing how that's changed. But the concepts are the same. It was harder to do that to a computer that takes up a whole side of a building. So here we'll go through the 12 rules. Information rule. Information should be presented in a tabular format, which it is. Here. We talked about, I think I did mention this in the last lecture, this is a table. You're used to seeing tables, even if you didn't know to call it that. You know, the attribute tables in ArcMap or Excel, where you have a spreadsheet in Excel, the table where you have columns and rows. The columns, as I mentioned earlier, the columns are attributes about the information and rows are occurrences of that. The information, the guaranteed access rule, information is not ambiguous. You know, if you ask for the same thing, every time you should get the same result. If I say how many states begin with the letter W, it might be 2. The database should always return to. If the data doesn't change, it's not a good database if the data stays the same and every time you ask the same question you get a different answer. That's no good. Columns should be allowed to contain, and I didn't mention this. Most databases do not adhere to all these rules and guidelines, but they're good general principles. Databases should be allowed to contain a null for a value. And a null value means there's no value. I'm collecting GPAs from students, or here's a good one. Someone blows off next week. What would I put in for your grade? A null, because you never took the test. So I don't have a value. I mean, I'd probably put 0 in that case, but in that case you haven't taken the test. So I can't enter a value in the column for test because there isn't a test for you to enter. So that would be an example of a null, no information. That happens all the time. And most databases don't honor this rule because sometimes we don't allow nulls. In most databases, when you're setting up a column, you can specify that the user must enter something, or you can allow the person to enter nothing. And that's actually good, I think, because you can make cases for each. There's situations where you want to force the person to put something in. And there's other cases where you want them to not be able to enter this null value or nothing. The user should have access to the catalog. In other words, you should be able to look up information about the tables, about like the names of the columns, whether they're number or text columns, and so on. I don't want to spend too much time on these. Database should have a sub-language, which is a programming language that allows you to build a query. So one example, SQL, we won't get into here. Have you done select by attributes in any lab yet? I'm trying to. Next week, next week you'll be doing select by attributes. And when you do, think of this. That's a query language that enables you to take a data set and query, ask for specific features that match your criteria. Find all states that begin with the letter W is a perfect example of a query, and ArcMap, along with any relational database, has a language built in that lets you ask those questions. The number 6 basically is there should be a way to do a join. You did that in lab this week. You should be able to change data. Insert a new bird sighting, for example, delete a record, or update multiple rows. Users should be able to, ArcMap layers are a good example of this. Users should be able to work with the data without necessarily knowing how it's stored behind the scenes. So if you have a join layer in ArcMap, you don't necessarily have to know about the joins and the location. You know, your ArcMap document that you open has layers loaded in it. You can work with those layers without having to know the storage location. And logical data independence is the same thing. Integrity independence is kind of like ArcMap, so you can make changes to layers in ArcMap without changing the data. You can change colors of dots. You can do a join. I'm sure they talked about that in lab. I'm sure that when you do the join in ArcMap, you're not actually changing the data. You're just joining how the data looks right in ArcMap. That function adheres to this number 10 rule here. Integrity independence. 11 isn't that important to me. There should be every good relational database. ArcMap doesn't necessarily follow. They should have security, especially in the work that we do. I was at the Navy last week. There's a lot of secure data, so that every relational database should have a password where users have access to the data only through a username and password, and you should be able to restrict access even further. We call it granular security, is a fancy term we'll use. In other words, you might say, if there's a specific table, Torsten can have access to it, but Kijun can't. That's called granular security, where you could actually assign specific individuals very specific rights to information in the tables. You can even say, you can do that in SQL Server down to a particular column. Where it's like, okay, I trust Torsten to look at this table, but this one column, I don't want him to see it. So that's granular security. Getting a little beyond what we want to talk to here, but I just want to introduce the topic of that. Any questions? So I've mentioned, here's the definition. I mentioned RDBMS a little bit, a couple times. To define that, first of all, DBMS stands for Database Management System. And RDBMS is a relational database management system. It's a database that follows these relational rules that I just started talking about. Microsoft SQL Server is an RDBMS. Oracle. I'm not expecting many. How many people are familiar with SQL Server or Oracle? Anybody? Okay, a little less than I thought. I wasn't expecting many. Those are commercial, very robust, high-end databases that are structured for heavy access. So you think about, here's an example. You go to take money out of the ATM machine. You have to put your PIN number in. Obviously, somewhere they have a record of every person in the world's PIN number. You think about that. That's probably a pretty big database. but it doesn't take long, does it? You put in your PIN number, it comes right back, accepted. So there are certain databases that are optimized for what we call very high usage, large databases, heavy traffic. Big data is a good buzzword like that is going around. They use these very complex RDBMSs like Oracle or SQL Server. They're designed for very heavy traffic and usage, where the ATM, at any given point in time, there has to be thousands or more people accessing that information, that database. And I actually stumbled on another point with that. An RDBMS lets multiple people use a database at once. It wouldn't be too good if some person in Beijing is getting money out, so no one else in the world can get money out until that person's done with their transaction. That wouldn't be too useful. If you think about it, that's a single user model. ArcMap shapefiles are a single user model. If someone in the lab opens up a shapefile to edit on the M drive, no one else can edit it. It's not an RDBMS. But in an RDBMS, it's set up in some cases so that multiple people can get in the database at once. And for something like the ATM example, that's critical for that to occur. Microsoft Access is an example. Hopefully more people have used, at least familiar with Access. That's an RDBMS, so it's a single user RDBMS. You can't have multiple people using it at once. So this is a screenshot of a Microsoft Access database. And this is actually the database I used for a lot of the relational database example screenshots that we're about to get into. And this is an example of a Microsoft SQL Server database. So these are all specific. This is from work, so these are all different clients' databases. So within the database, there's specific tables of information. These are from Colorado, where they have Weld County, different Larimer County, different county GIS layers. So these are RDBMS, and one big difference, a shapefile is a flat file. The lab instructors say, here, go to the M drive, here's your shapefile, you look at it, it's one file or a couple files. An RDBMS actually has multiple tables within it. You can see here. There's another difference between a flat file and a database. So I said normalization is a design technique in relational databases. It's a process you go through. And we'll go through an example in a second. We got a sneak preview in that introduction slide. The normalization is based on the concept of normal forms. A table is particular normal form if it satisfies a set of rules. And we'll go through this and it'll make sense. I have been known to ask you to normalize a table that isn't as fancy as these, and sometimes that's one of the harder questions on that first test. I think it's good that it's right before the test when we cover it. So in a relational table, a column is functionally dependent on another attribute. So that means every table, every table should have a column, call it column X, it's a key. So let's pick up from the example I started. This is the key. Very often, not always, but one convention to name the key, it would be the table and then ID after it. Observer ID in this example. Did I mention? Yes. So the primary key of the relational table uniquely identifies each record. Each value must be unique and cannot repeat, or that violates the normal form rules we just talked about. So you see here, 1, 2, 3, 4, 5. I can't have two number 2s. And number 4 specifically identifies GIL. GIL is paired to the number 4. We can't ever change that. You don't make GIL number 5, and you don't add another burner and also call them 4. The ID, the key field in the column needs to be unique. It should also, okay, that's on the next slide. I was worried. it should never, ever, ever change. Anything that can change should not be used as the key. And I have seen that mistake. I've made that mistake and seen others make the mistake over and over. I've done it myself. Because anything that can change could, think about, and you'll see this more as we go on, all these different tables that relate to each other. If the key changes in one of them, the link is lost forever. So things like names, none of the other columns in here would be a good key. As we saw with Prince, even a name can change. And obviously, if someone gets married, they don't have their maiden name anymore. Name is not a good key, and obviously, name can be duplicate too. Just about everyone, I'm sure everyone in here has someone else in the world with the same name. So name can change, name can duplicate. Name is not a good key. And the term for that you'll see sometimes is it's immutable. And for that reason, I've also seen the key should be what's called dumb. And by dumb, I mean the key should have no meaning. Because if you think about it philosophically, anything with a meaning could change. A phone number, the address could change, years of experience will go up by 1 every year. Their list of birds seen will go up as they see a new bird. The only thing in this column that will never change is this ID. Does that make sense? And maybe you understand why that's so important. You have, those of you that are citizens of the United States have a social security number. And the social security number is a dumb key assigned to all U.S. citizens. I mean, your name may change. Many of your names will change. Your social security number, unless you're doing something you shouldn't, your social security number never changes. So imagine the government has a lot of information about you. In the last couple of years, we found more than we knew, unfortunately. But there's a lot of different tables of information out there about you. Your health records, your UB records, your employment, all out there. If when you get married, someone has to go through and update all those tables, it could easily get lost. Your social security number never has to be updated. So the social security number is a great dumb key for every table. So every government record about you, again, if you live here, has that social security number. There's no meaning behind a social security number. I've actually been told that there sort of is, but it will never change. It has to do maybe with the year you were born or the location. I don't know if that's true. But I always say, I think the social security number has no inherent numerical meaning. So there's no reason why you can't keep the same social security number your whole life. And that makes it a good primary key. Does that help out explain? Hopefully that helps to explain the importance of primary key. And often that's a question because I think that's a really important topic. At Erie County Water Authority, sometimes I pick on them, but I've been there for 20 years, so I have a lot of stories. They have a database of hydrants. If they have to go out, especially now, a lot of them are freezing in this kind of weather. So they keep track of maintenance. They also bill towns if they lease a hydrant to a town, they bill the town yearly. So they have a code. They have a grid system where it starts at A01 is Amherst, you go down Chickawaga, A02, and so on. If I had my marker, I'd draw it. So they have, pre-computer even, they had this grid on a Mylar, clear sheet of paper. And when someone would draw a new hydrant, they would take the Mylar with the hydrant on it, put that's the original GIS pre-computer, put the other clear sheet of paper over it and say, oh, that hydrant is in grid D25, D01. That's the key. So they would assign that as the key. So what happened over the years is, this guy was a little sloppy when he threw the thing down. It's 4:59 on a Friday. He said, close enough, and it's actually in DO2. But he didn't do a good job. So 30 years later, a diligent GIS person like myself comes along and says, oh, that's in the wrong grid. I'm going to fix it. So I change it in the GIS layer to DO2, and I've lost all links to the other tables. Because in the other tables, it still says DO1. And so that problem started because it shouldn't have been linked by that value because it can change. It should have just been hydrant 26 or hydrant 226. That way it can be hydrant 226 forever. And that grid attribute can be a different column, just like these are different hopefully that story helps illustrate too. Actually, I wonder who made that mistake. I can't imagine who that was. It's Greg, we lost the data. Just trying to help. The first normal form must not have, I talked about several stages of normalization, and we'll start by going over no-nos. The first no-no here, there must not be any repeating groups, and people do this all the time to try to save space. This is an unnormalized table that's violating the first form, normal form. So we've got a scarlet tanager, a crane sighting, and a woodpecker. And for blue grouse, like, oh geez, we had 2 sightings. I'm going to save time and just put them on one line. You know, that's a no-no. Every row should represent one occurrence. So what if we wanted to query? What if I wanted to go to query find every sighting in the year 2003? That's not going to work because it's not a valid date. So this is a no-no here. There should be a 7th line. There should be 2 separate lines for blue grouse. Every record should be one occurrence only. Makes sense? So that's the lowest level violation. And oh good. On the next slide here, I split this out. I now am adhering to this first normal form. The 2 different sightings of this bird in Arizona and Colorado have been split out into 2 different records. Important for database integrity. Any questions? Does that make sense? And you'll see another problem though is we'll get to that in a second. I don't want to talk about that yet. So to satisfy the second normal form, it must satisfy the first normal form before you can get to the next level. Again, each row representing one record. This example does not satisfy the second normal form because you have 2 separate. Every record should rely on the ID. And we have 2 separate. The Latin name is tied to the species. So here, again, this is our sightings table again. And I picked this because I'm a nerd, because this actually did happen. They did change the Latin name of the blue grouse. Through some DNA, I think they discovered it's actually different species or belonged in a different genus. For any biologists here, that's actually happening a lot with DNA analysis. They're finding birds that you wouldn't think that are related, that are very close, and yet there's other birds that look and act exactly the same that actually are not related at all in the evolutionary tree. DNA is telling us this. So in short, they had to change the Latin name because the grouse was in a different group. So now, because this doesn't adhere to the second form, I'm going to have to find every occurrence of the Latin name. And if I change it in just one location, I now have this blue grouse with the correct Latin name, that blue grouse with the old name still. So that can't be. So here, also when you add a new row, you need to determine the value of both columns to add a new row. And we don't necessarily, shouldn't have to do that. So, here's how I would split that out. I now have a birds table. Instead of listing blue grouse over and over, I have another table where I list each unique occurrence of a bird. And then now, going back to a couple slides ago, each Latin and common name relates to the bird ID. Bird ID number 3 is Lewis woodpecker, Melanopes lewis. Lewis and Clark discovered that. So now I'm adhering to that second normal form. And here, I haven't updated it yet here. So instead of having the redundant data in your first table, I can take advantage of this bird table. Some of these are a little out of order. And we'll do that in the third normal form. So when we start using this birds table, we'll be satisfying the third normal form. Each row in a table only references one specific entity. This makes the database very complex, as you'll see when we're done with this exercise. And that's where the GIS person complains, why can't you just give me one file? But hopefully through some of the stories I've told and examples, you see why that complexity can be a good thing. So I guess we'll start over a little bit just to review. So here we're back to having a separate row for every specific bird sighting. But remember, for the third normal form, we want to only reference, in each table, we only want to reference it one item, and we shouldn't repeat any items. And you can see a bunch of repeating information here. Repeating birds, repeating locations, and repeating observers. So here I have split up, like I started to introduce a couple slides ago, I split up birds into their own table called birds, and I assign a dumb key, just a random number that doesn't repeat and doesn't have any meaning to the birds table. And so then I will, going back to our sightings, I can remove those two columns from the sightings table now and just reference the bird IDs. So now, in our new sightings table, I have the observer. Well, I haven't done that yet. I have just a bird ID. So blue grouse, for the two blue grouse sightings, for the two dipper sightings, it just says 6 and 7. Right here. So it's much easier if they actually did that. See, I was thinking we had the blue grouse got changed to the dusky grouse. I don't know why. They do things like that. They change the names of things. So I only had to change it to dusky grouse one spot because this data is normalized. That makes sense. So if any of this data changes, I only need to change it in one location. Next thing, and I alluded to this, I still have the observer. You see there's still duplicate data. We've got 12 bird sightings, but only a handful of birders. So that's another potential duplicate data. So let's normalize the bird sighted, the observer. So now I add another separate table called observers, where I give an observer ID. You'll get a dumb key, sequential number, and then the names of the people here, and the items specific to that observer are in the observer table. So home address relates to the observer, not to the sighting. So the home address is in the observer table. When we get done with this, the only things specifically related to the sighting are going to be left in the sightings table, and everything else has this other link. So now we have, and unfortunately you start to see an unfortunate side effect is the core tables in a normalized database are harder to read. And that's unfortunate. I mean, it's a necessary evil. I mean, it's hard to look at this and understand what's going on. But that's why you have joins, and that's why you have views that we talked about, so that you can construct. One of the COD's rules was, what's going on behind the scenes should be transparent to the end user. You have this all in the background, but you set up a table for the user using the joins like you did in lab. So it looks like it's all one big table. So the end user can be happy. They can click on a sighting and see all the information. But behind the scenes, transparent to the user like the COD's rules, it's being stored efficiently. Make sense? And then the final thing here, you'll notice some locations duplicate. Estes Park, Colorado occurs 4 times, and so on. So we can bring that out, make a separate table called location, and normalize that. And so now our resulting normalized database has 4 tables. Each table has its own primary key, and as I mentioned, each table only has attributes about its own subject matter. The birds table solely has the name of the bird. There's 2 columns for the English name and the Latin name. You could have columns for other languages if you wanted. The location table only contains its ID and the information about the location. And you could have other things, country, state, fair, and so on. The observer table, again, only contains information about the observers alone. And the sightings table just contains references to this key that can be joined. So just like you did in lab this week. That makes sense. So again, people will cringe at me when they get that, and that's just a bunch of numbers. But hopefully now you can see the reasons for doing it behind the scenes, and that's why joins exist, so that to the end user, I should have had another slide to illustrate that point. You can use joins so that the end user still sees something like this. They don't know about all these 1s and 2s and 3s in the background. They still see a combined table, and yet, however, it's still being stored efficiently behind the scenes. Any questions? 7:20. So some of I've probably touched on these throughout the discussion, but some pros and cons. This is sometimes a good question too. What's good and bad about a relational database? It's very flexible design, very efficient. You can see how you're storing a lot less. If we had time, which we don't, I could set up as an exercise, counting how many characters are in this database versus an unnormalized table. And I think you would find, even in this small example, there's a lot less characters to store here. But now extrapolate this and think of it as a table with 1 million records, and think of how much space it would save. And of course, it's very flexible for updating, eliminating redundancy, making an update easy. Like the example where I changed the bird name. I only had to change it at 1 location. So those are the pros. Setting up searches and setting it up so the end user can use it can be time consuming. Now I have to build all those joins like you learned in lab. If it was just 1 file, you wouldn't have to build joins. So that's a con, I guess. And it's complicated, as we saw. It's not conducive to browsing. As I said, it's very hard just to go into this and see what's going on. It's all just a bunch of numbers. So I've really talked up the relational database. I don't mean to suggest that it's always appropriate. If your data is mostly about one thing, maybe a flat file like a shape file is fine. But the more complex your database, the data you're collecting is, that sort of tips the scale towards a relational database. I don't really want to get into that. We can ignore that object-oriented data model for now. What time is it? Oh, it's not that late yet. It seems like it is. And we will talk next about, are there questions first? Good. Map scale. I guarantee a question on this. Very important. You've probably covered or at least seen that. Even if you haven't explicitly covered in the lab, you've probably noticed the scale displaying on ArcMap and how that works. You know that oh wait, no, I can't. So map scale, simply put, is the ratio between the size of the feature on your map and the size of the feature in the real world. So in the simplest form, if the map scale is 1:1, your map is as big as the real feature. If I trace this desk, and so the desk is this big on the paper, it's a 1:1 ratio. The desk is the same size in reality as it is on the map. If I drew a desk on this back of this journal and the desk is about this big. Now that's maybe like a 1 to 10 ratio if you think about it. The desk is 10 times bigger than the sketch that I've made on, which I didn't really make, on the piece of paper. Obviously we're dealing with a lot bigger scales on a map. So in this example, I have, and this is printed out, it's more than 3 inches on the projector. So on the map screen here, on my map, there's about 3 inches between Buffalo and Rochester. Obviously it's quite a bit further than Buffalo and Rochester are more than 3 inches apart in reality. They're about 60 miles. So if you do a little bit of math, you would say on this map, again on the screen, the projector messes things up. 1 inch equals 20 miles. So on a projected coordinate system, you can consistently measure, you can measure the distance of a location on Earth to another location based on the distance on the map. And you see here, here's a rudimentary scale bar. This location, or this distance on this map is 2 miles. So from UB to Dust, I ate today, so there won't be as many food references. It's about 2 miles. And you can tell based on this scale here. As I zoom in, or zoom out, the same distance on the screen now represents a much wider distance in reality. Now that same distance represents about 100 miles. So this is confusing. I think I have a slide on it in a few minutes. I'm sorry, this won't be on the recording. I'm recording on my laptop. This map has been zoomed out to a smaller scale. A smaller scale map is further away. That always confused me. To me it seems like it should be the opposite. That's a small scale map. The small scale map also has a larger scale numbers, we'll see. Where this is a large scale map of downstate. And you can see the same distance on the projector, the amount of real world distance that it represents is changing as I change map scale. Sometimes map scales are represented with 2 different units. Like the example I just gave on the previous slide. You know, one inch is equal to 20 miles. If you have, I should have brought a Rand McNally or something for my prop today. You'll see in the corner, it'll say something like that on each state map. It might say 1 inch equals to X number of miles. Next time you use if anyone has paper maps anymore, this is moot. You know, if you still have any paper maps you haven't recycled yet, look at them and you'll see in the legend they have, you know, that will be mentioned. So that you could, if you want to take out a ruler, you could measure an inch on the map using your ruler and you know exactly what the real distance is. I think there's some engineers in here. Engineering drawings often have a standard scale on them, and this is used a lot. You know, for example, 1 inch equals 400 feet. An engineering drawing might cover a much smaller space on Earth, say a new subdivision, for example. And a subdivision map that's being plotted out by the engineering company designing the roads and the sewers and so on might have a scale of 1 inch equals 400 feet. So on that map, you could take out your ruler, measure an inch, and you know that it's 400 feet. So as I mentioned, I put that on there, I did. These are 2 different units. Inches to miles, inches to feet. A simpler way, though sometimes harder to visualize, to represent map scale is through just a pure ratio. And GIS scales are often converted to ratios by default in ArcMap. When you see the scale in ArcMap, it's a ratio. When I first introduced this I said I drew a map of the desk. I used a ratio. I said, the desk is 10 times as big as what I drew here. So we can convert between, and this makes a good question, always. You can convert between the units model like that and a ratio. So in the first example, if you zoom to an inch equals 20 miles on ArcMap, it's by default going to give this number. Although you can change that setting now in version 10. And how did I get that number? Well, you multiply or divide one side of the equation to get the same units. So 20 miles is 20 times 12 feet. But 20 miles is 20 times 5280 feet, because there's 5280 feet in a mile. And then times 12, because there's 12 inches in a foot. Does that make sense? See what I'm doing there? So I'm converting from miles to inches by multiplying by 5280 and then by 12. 5280 gets us to feet. Another 12 gets us to inches. And that, if you multiply 5280 by 12 by 20, that's the number you would get. Now it's inches. Now it's 1 inch equals 1,267,000 inches. Now, because the units are the same on both sides, you can drop off the units. At that point, it doesn't matter. It could be an inch equals 1.2 million inches. It could be a foot. If an inch on the map is equal to 1.2 million inches, then a foot on the map is equal to 1.2 million feet. Does that make sense? So once the units are the same on both sides, you can drop off the units and just consider it a ratio. A simpler example, an example more like I would be likely to ask on a test would be something like that. It's a little easier. Where 1 inch equals 400 feet is a scale I've seen in a lot of engineering drawings. 400 times 12 is 4,800. So 1 inch equals 400 feet in ratio is 1 to 4,800. Does that make sense? Good. Oh, good. I have here's a screenshot of ArcMap showing the current scale. And I did set ArcMap in the screenshot to be 1 inch equals 20 miles, and you see that it's at that 1,267,000 ratio value. And you may have noticed ArcMap also gives us a set of commonly used scales that we can use. So on this map, the distance between Buffalo and Hamilton in reality is 1.2 million times further than the distance on the map. I don't have to bring this up again, but here's a screenshot. I already showed you Google, where Google Maps shows you scale represented at the scale bar. So in the scale bar, that says 500 feet, so you know that distance on the map is 500. No matter where you put your finger on the map, it's 500 feet. We're going to do a full review after the break, but I put in some other review examples tying into previous discussions we've had and preparations for the test. I probably will ask something like this. Remember we talked about vector data? Points, lines, and polygons. The points are 0 dimensions. Lines are 1 dimension. Polygons are 2 dimensions. I have some examples of, and we talked about this in class. I think you even gave me some examples of where you would use each feature type in reality. So the U.S. Census data, I downloaded a data of shopping centers, I think in Arizona. These are represented by points. So this is a point vector feature test. And this sort of reviews what we talked about 2 or 3 weeks ago. I don't remember which lecture it was in. So those are 0 dimension objects. It's just a point representing, Chandler Festival. And I can't read the rest of these. Arizona Mall. The Arizona Mall is just represented with a point. a one-dimensional vector shape is what we would refer to as a line. And here's an example, in Arizona and New Mexico, I have interstate highways as a GIS data set here. These are lines. I'm not representing a width. It's just a line, say, between Phoenix and Tucson and so on. So this is a one-dimensional line vector feature. And we talked about that second dimension being an area, or you'll hear me call it a polygon. You hear GIS people call them polygons or area. These are the counties of Arizona and New Mexico. So a polygon or an area is two-dimensional. It's a line that connects back on itself having an internal area. So Maricopa County is defined by a line that closes, and everything inside that line is Maricopa County. Everything inside this slide is Pinal County. And a two-dimensional vector shape has an area to it, whereas a one-dimensional shape like the line only has a length. We can't calculate we can't calculate an area to a one-dimensional feature, only a length. But counties, which are polygons, have areas. Okay, any questions? Feature type selection. So, whoever created the shopping center data set chose points. We chose lines for the highways, polygons for the counties. You might have already started to think about this. But when you're first creating your data, what type of feature you select might depend on the scale. And now you know what scale is. The scale at which your data is mapped might affect what type of feature you choose. A feature class can, and this is unlike, I think there are a couple AutoCAD users here. A GIS feature class can only have one type of shape in it. So in other words, those counties, and this might seem obvious, but I think it is worth making that point. The counties layer can only have polygons in it. You can't put a point in this layer or put a line in it. Conversely, the other types, this data set has lines and only lines. In other words, you cannot mix types of features in one GIS vector data set. It's either points, it's exclusively points, exclusively lines, or exclusively polygons. So you need to think about that when you're creating your data. Pay close attention to scale. And the screenshot that I have here demonstrating that is, and as I mentioned here, because of that, the same feature may be represented with different feature types depending on the scale of your map. An example here, I think I'd rather do that backwards. Here's a map of the United States, and I've identified the capital of Arizona, Phoenix. Seems like a dot is appropriate, isn't it? So I've used a point to identify Phoenix on this map because of the map scale. But I also have a layer. This is zoomed in. This is municipalities of Maricopa County. I should have chosen a different color. But now on this map, I've represented Phoenix with a polygon. Because at this scale, I can clearly see the boundary of the city of Phoenix. It wouldn't be appropriate to try that here. You wouldn't be able to see, all you can really see is the dot at this scale. You're not going to be able to see all the exact boundaries at that scale. So it's an example of using two different feature types. Does that make sense for the same object? And we even see that on Google. Google has features stored in two different data sets, no doubt. At this scale, they're representing Buffalo with a dot. See, Buffalo is a point here. But as I zoom in, at some point, there we go. Let me get this out of the way. Oops, I didn't want to get that out of the way. At this scale, I can see a representation of Buffalo as a polygon. see this kind of lightly shaded red area with the red outline. That is a polygon representing the boundary of the city of Buffalo. It's interesting when they turn it off. At some point, okay, at that scale, they switched it to the point, the marker that Google's famous for. When you zoom in, they've decided that's the threshold they've arrived on, where they draw it with a point at a smaller scale than that. And then zoomed into here, they decide that now they've switched the feature type to a polygon. So I'm sure, I don't work at Google, but I'm sure that they have two separate layers in the background here. And then when you zoom into that scale, they switch layers. They switched from the point layer to the polygon layer. Now that we're in close enough where you can actually see the outline. Any questions? Got some more slides, a couple new slides, a couple review of earlier topics. We'll take a break and then we'll come back and go over the 3 previous classes slides. And I'll kind of, obviously quicker than that. We're not going to be able to cover 3 nights in an hour. We'll go over it quicker, but that'll give me a chance to really focus on what I think are the key points for us, for you to think about for the test. So here, the slide, and I stole this from Esri. In their ArcGIS 1, they have a slide similar to this. When they started saying where the importance of a reference system, like projected coordinate system. So we talked about projected coordinate systems early on, and I'm kind of reviewing the importance of that, the importance of having one. If I ask you where this rectangle is, you can't tell me where, unless if someone raised their hand and said it's on the screen, and I know that it's on the screen. But if I asked you where it is on the Earth, there is not a way to tell. There's no reference. No one can definitively answer, oh, that's in Germany, that's in China, that's in Buffalo. You don't know. There's no reference. Where now, it's been projected and there is a reference. It's in the Ellicott complex. Now you can answer the location of the rectangle. I didn't copy it, the Esri slides go a step further. They have another slides where it just shows this, and it shows a tree. And they say, well, it's 50 feet from the tree. And their point was, it still doesn't answer the question, because 50 feet from the tree is relative, because you don't know where the tree is. So maybe I should put that slide in that they have. Whereas here, now the location is definitive. And I mentioned that a couple weeks ago. There's only one location on Earth that's the Ellicott complex. So if I identify the coordinates of here, there's not someplace else there isn't someplace else in this projection on the globe with that coordinate. With a proper projected coordinate system, every location on Earth has a unique coordinate that only applies to that spot. And so that's kind of the point from all these slides. And to review, this is an important one. The difference between, and you'll see this even using an ArcMap. I'm sure you've done this where you set a projection. The very first question, or not yet, you will. You will choose either geographic coordinate system or projected coordinate system. We'll talk about we'll review the difference of those. The difference is a geographic coordinate system is spherical, and we did talk about that, I think, the first night. A geographic coordinate system is measuring the location on a sphere with latitude and longitude. The projected coordinate system is projected onto a flat surface. So those are the 2 main types of coordinate systems, and often that's a question of what is the difference between a geographic and a projected coordinate system, because that's a pretty important one. So some of these are repeat, but I think it's important. A geographic coordinate system, as I just mentioned, is based on a perfect sphere. And we talked about how datums map a non-perfect sphere like the Earth, which is not, it's more of an ellipsoid. And locations are read as latitude and longitude. We'll have some slides on that in a second. And we have latitudes are parallels, longitudes are meridians. That's where we talked about the 100th meridian song. Is actually goes through the Great. That's what the song is about. Goes through the Great Plains. 100, and that's 100 degrees west of Greenwich, England, on the circle. Goes through Manitoba, North Dakota, things like that. Some important terminology for geographic coordinate system. Some of these things you've probably heard of. We don't like to be at the equator right now. The equator is the east-west line around the center of the Earth, measured 0 degrees latitude. You can see it pictured here. And other lines on the equator, other lines going up north or south, up or down from the equator, are called parallels or latitude. And you can go from 90 degrees south is the South Pole, 90 degrees north is the North Pole. So if you think about that, that's 180 degrees. And think about walking from the North Pole to the South Pole, you'd walk around half the globe. And a circle, for math class, has 360 degrees. So half of the globe would be 180. And this might be 30 degrees south, 30 degrees north. 0 degrees is the equator. And to help with this a little bit, I'll bring up Google Earth, like I did the last time. The equator is pretty easy for geographers to pick out. It's the middle of the Earth. The meridian is a little bit more arbitrary. The meridian is a line across around the globe this way. So they've chosen, millennia ago, they chose the prime meridian, or the 0 degree meridian line goes through Greenwich, England. And lines of longitude or meridians are east or west of Greenwich, England. So the meridian in the song is 100 degrees west of Greenwich, England. So that's somewhat less, it's roughly a third of the way, when they talk about the Great Plains, that's roughly a third of the way west of England around the globe, if you picture it that way. So you can see, that shows up a little better. The prime meridian is in yellow there. You can see that's 30 degrees west, 50, 70. We're just shy of 80 in western New York. There's that 100th one going through the Great Plains. And if you have a hard time with on the other side of England is the international date line, essentially. That's 180 degrees. If you think of walking around this way, if you walk around from the prime meridian to the opposite side of the Earth, you've walked 180 degrees. So 180 degrees east and west converges on this international date line in the Pacific Ocean. So notice there's 170 degrees west, 170 degrees east. They converge. So 180 degrees east and 180 degrees west are the same spot. If we met at Greenwich and start walking our separate ways around the globe, we would meet at this location, assuming we walk at the same pace. Again, this is somewhat review. This is a good time to go over it. So just some examples, if you go from the equator to North Pole, so the North Pole is 90 degrees north, that's a fourth of a circle. So a circle has 360 degrees. So that's a quarter of a circle, so 90 degrees. So if you start at 0 degrees latitude and walk to North Pole, you walked a quarter of the circle, or 90 degrees. So once again, here's some screenshots showing that. We're right around 43 degrees north here, so we're just shy. It doesn't feel like we're actually slightly closer to the equator than to the North Pole. Although you could fool me about that today. And for the last month. So these screenshots kind of reinforce some of the things I've been talking about. Latitude is meant, so just to summarize, latitude is north or south from the equator, from 90 degrees south to north. The length of the length of the latitude is constant everywhere. A degree is about 69 miles. If you divide the distance from the globe, from the equator to the North Pole by 90, you get roughly 69 miles. The 43rd latitude goes roughly through just north of UB. We're very close to it. The 42nd latitude is the border between New York and Pennsylvania. If there's anyone here from Jamestown, that area, you know, you're about 60, 70 miles from home. It's about 69 miles between degrees. Longitude that starts Greenwich, England, goes east and west. The length shrinks. So you can't. A degree of longitude is not constant, and you can see that on this map. I mean, these are 10, I think, at this scale. So the 10 degrees of longitude at the equator is quite a considerable distance. But notice how that 10 degrees becomes smaller as you approach the pole. In theory, at the North Pole, just next to the North Pole, 10 degrees of longitude might be like that far apart because they all converge. So I think I mentioned in the very first class how that makes latitude and longitude not a very good measurement. And that's why we have these projected coordinate systems. So I think when we review the first class, we'll go over this. I usually do ask a question converting between degrees, minutes, and seconds. I'll hold that for the review because there's some more slides about that there. I'll choose easier numbers to use than these horrible ones. So just to review quickly, there are 60, just like a clock. Just think of the degree as an hour if you have a hard time remembering. There's 60 minutes in a degree, just like there's 60 minutes in an hour. And then there's 60 seconds in a minute. So that latitude, I think that's UB again. 57 minutes is almost 60. So you can tell just looking at that we're just south of the 43. In essence, 42 degrees, 60 minutes is the same as 43. Just like you would never say 7 hour or 7 o'clock. You'd say 7:45. If you said 7:60, no one would say that. You might say 7:59. But if you think about it, 7:60 is the same as 8. It would be 8 o'clock. So 42 degrees, 30 minutes would be 42.5 in decimal degrees. I'm going to have some more slides on that that we'll go over. Usually on the test, I'll ask easy things like that, like 30 is 0.5 and so on. You know, I've decided I'm going to this gets into talking about programming. I do the GEO481 class if anyone's interested next semester, but I think I'm just going to blow this off. I've decided I'm going to take it out of the course. There's too many other things to talk about. So what we'll do, we'll take a short break. When we come back, I'll go over the previous 3, I think it was 3. I'll go over all the previous 3 lectures, kind of review for you what I think is important. And then if you do leave, we'll see you at class time, 6:30 next Tuesday. But hopefully you stay. We'll review all the key points. We'll meet back up in 5 or 10 minutes. I'm sorry? No, I just go through the previous classes.